let's discuss the difference between an intermolecular force and an intramolecular force. So the types of forces that we've been looking at up to this point in general chemistry, all through general chemistry 1, for the most part anyway, were intramolecular forces. We did look a little bit at the very end of Gen Chem 1 about polarity, and we're going to get into that a lot more here. But we did talk a little bit about polarity inside of a molecule, but we didn't really extend that to outside of the molecule, how it affects other molecules, at least not very much. I believe I just briefly mentioned it, but we didn't get into it much at all. Now we're going to dive into that really in depth here. So an intramolecular force is any force that exists and is only affecting things that are inside of the molecule. So for example here, the bond between the hydrogen and the chlorine, that is a very strong force that is holding those two atoms together, but because it exists inside of the atom, or sorry, inside of the molecule, that is what we call an intramolecular force. It is only affecting things inside of its own molecule. An intermolecular force is a force that exists between two different molecules. So intra is between two different things in the same molecule. Intermolecular forces are between two different molecules. So the attraction that exists between the chlorine in this molecule and the hydrogen in this molecule over here, that is an intermolecular force. Now it says here that this is a weak interaction, and this is all relative. All the strengths and weakness of forces that we're going to be looking at here, it truly is all relative to one another. So when we compare a covalent bond to this interaction, it is indeed very weak. But if you compare this interaction to something like dispersion forces, which we'll see in just a second, this is actually fairly strong. So it is all relative. What we're looking at here, it's strong or weak compared to what. And what we're going to mainly be focusing on is exactly how do these forces exist, what causes them to exist, and then what are their relative strengths one to another. So another example here of an intermolecular force, there is a force between the hydrogen on this water and the oxygen on the water over here. And that is a force that is actually stronger than this one. But it is still much weaker than a covalent bond. So this is also pointing out another very common, and actually not just common, it is absolutely true, that intermolecular forces always exist over longer distances than intramolecular forces. There's actually a really good rule of thumb when it comes to bonds that we talked about in Gen Chem 1, where the shorter the distance is between two things, the stronger the interaction between them. So if you have two things that are really close to one another, they're probably interacting in a really strong interaction. There's something very strong holding them together, whereas if you have two things that are really far away from each other, that's going to be a weaker interaction. And so intermolecular forces are always on a very longer distance. They're over a longer distance. And depending on who you ask, actually, there is some disagreement over what constitutes intermolecular versus intramolecular, because there are a few very specialized molecules where it is kind of iffy as to, like, are these actually two different molecules, or are they just one molecule that are just kind of two different parts of it are kind of far away from each other and the bonds just break really easily. And so most people actually will qualify, they'll determine if a covalent bond exists by actually the distance over which the bond is taking place. So the distance between two things that are interacting is actually fairly commonly used as the ruler as to whether or not two things are technically bonded together. But that's beyond the scope of this course, so we'll just leave it for now at intermolecular bonds, very far away from each other. Intra is always very short distances. So we're going to look at 4 different types of intermolecular forces here. Not all in this video, that would take too long. We're just going to look at that first one, and then we'll look at the other ones in later videos. So we're going to be looking at dispersion forces, dipole-dipole forces, hydrogen bonding, which as we'll see is actually just a special type of dipole-dipole interaction, and then ion dipole, which is like a souped-up version of dipole-dipole, but it's definitely different enough that it gets its own classification. So these 3 are kind of getting more intense as you go along from one to the next. Dispersion forces are kind of a unique type of interaction that's not exactly the same as the other 3, but is not completely out of the ballpark either. So let's talk about those. Let's talk about dispersion forces. The first thing you need to know is, depending on where you look, whether it's in our book or a different book, or if you look online, there are multiple different names for this kind of an interaction. Some people call it dispersion forces. That's what I'm going to do my best to call it every time I mention it. But when I was taught about this, I was actually told that it's called induced dipole forces, which is a mouthful. So even though that's the way I was taught, I prefer dispersion forces. For no other reason, it's easier to say. These are also often called London dispersion forces, or just London forces. So there's multiple names, but they're all just describing the same phenomenon. Essentially what a dispersion force is you have 2 different atoms, or molecules, or whatever the case may be, but just for our purpose here, we're going to look at atoms. These are specifically helium atoms. So the helium atoms have 2 different electrons. They're floating around in this space in here, not necessarily in a circular motion like this, but they're just floating around in here. And depending on when you look, they're going to be relatively evenly distributed throughout the whole atom. Because remember, electrons, sometimes they exist as particles, sometimes they exist as a wave function. If we're not looking at it, it's going to exist as a wave function. And that wave function can vary from one side of the atom to the other. So sometimes the electrons are evenly dispersed, and sometimes, like over here, you'll have a split second where the electrons are a little bit more on one side of the atom than the other. It's not, and again, I'm not necessarily saying that the 2 electrons are on one side and there's nothing on the other side. Again, there's a whole field here of probabilities of where the electrons could exist. But for a split second, there is more electron density on one side of the atom than the other. And what that ends up doing is it gives you a tiny little dipole inside the atom. Because you have a little bit more electron density, in this case on the left side, that leaves a little bit of a positive charge on the right side. And if this happens to be near another atom, when this happens, what will happen is the electrons in this atom will be like, ew, what is that? What is that negative charge over there? That's a like charge. And if you remember what like charges do, like charges repel. So the electrons in this atom say, ew, I want to get away from those. And so the fact that there's a little bit more electron density on the left side of this atom pushes the electrons in this atom over to the other side, inducing a dipole in this one. And so now that there's a dipole in both, now there's actually an attraction here. because we have a little bit of a negative and a little bit of a positive. And so they're going to stick close to each other a little bit more than what they would have without that tiny dipole. Keep in mind here, this is a very tiny dipole, and this interaction only occurs for a tiny fraction of a second. So it's a very weak interaction that happens only for a very short period of time. This is by far the weakest of all of the types of interactions that we're going to look at on a single interaction by interaction basis. So one dispersion force interaction is practically nothing compared to a hydrogen bond, for example. But the one thing that dispersion forces have going for them is that everything can have dispersion forces. If something has electrons, it is capable of having dispersion forces. And this is not true for any of the other kinds of intermolecular forces. All the other intermolecular forces, there are set conditions that have to be met for those forces to be able to be created, for them to happen. Dispersion forces, all you need is electrons, and everything has electrons. Well, practically everything except for like helium-2+ and H+, and that's pretty much it. Everything else has electrons, and we are not going to worry about these two. So don't take that as, oh, he's giving us a hint, he's going to try and trick us later. No, I'm not. We're never going to talk about those again in the context of dispersion forces. So everything has dispersion forces. If it has electrons, it has dispersion forces. And we can see dispersion forces at work when we look at something like the boiling point of noble gases. Noble gases have no need to interact with anything else. If you remember that they have their valence shell full, that's the reason why they're very inert. Again, this is stuff from the last couple chapters of Gen Chem 1. They have a full octet. They are very happy. They don't want to interact with anything. They don't want to form bonds with anything. They are happy the way they are. So because they're not trying to chemically interact with anything, any difference that we see in the boiling point here is not necessarily going to be because of chemical differences, because chemically they're all the same. They're all just inert. It's going to be because of how they're interacting with the stuff that's around them, but not in a chemical way, just in an intermolecular forces way. And so what we can see here is that helium has by far the lowest boiling point, and as we get to larger and larger and larger atoms, the boiling point significantly increases to the point where xenon is at 165 Kelvin, which is still, don't get me wrong, it's still really cold. That is really freaking cold. Like that would kill you cold, like kill you very, very fast cold. But it's still way hotter than 4.2 Kelvin, which is like that's so cold that it's getting close to the point where it is actually physically impossible to get any more cold. But the reason for this increase in the boiling point is because the dispersion forces are increasing as we go from one to the next to the next. We can think about any of these boiling points, or even melting points actually, but most of the time we're going to look at boiling point as a measure of how strong the intermolecular forces are. Because if you think about what happens when you boil something, you're taking it from the liquid phase and you're forcing it to go into the gas phase. When it's in the liquid phase, all the molecules are really packed in close to one another. It's kind of the very definition of the liquid phase, what we talked about earlier. All the molecules or atoms or whatever they are really close together inside whatever container they're in. And then when you heat it up and force it into the gas phase, they are no longer really close together. They're a gas, they're floating around freely in the air. They'll bump into other things every once in a while, but they're not constantly in contact like they are in the liquid phase. And so to get something from the liquid phase into the gas phase, the thing that's fighting against that, the thing that's trying to stop you from going into the gas phase, are the interactions between these molecules. There are interactions that are holding them together. If those interactions are really, really low, so essentially the molecules or atoms have no interest in each other, they're not attracted to each other in any way, there's very, very weak intermolecular forces, well then you don't have to put very much heat into the system to boil it. This is why helium has such a very, very low boiling point. You have to put just barely any energy at all into helium to get it to go into the gas phase. And again, that's because there's so few electrons in helium that there's very, very, very tiny amounts of dispersion forces. Whereas in xenon, which, let me see, how many electrons does xenon have? It's really big. Let's see, 54. So xenon has 54 electrons, and they're spread out over a much larger volume. And so it's not only are there more electrons to move around, but there's a larger space over which to move them. And so you have stronger dispersion forces in larger atoms and molecules. And this also varies by the shape as well. So if a molecule has a shape that is really conducive to having a lot of surface area to interact with other molecules, then the dispersion forces will also tend to be higher. So in this example here, you have all this area where the electrons can push each other around, whereas over here, it's just that. Just this little area here. I don't know why it keeps thinking I want to do that. There we go. No, it still wants to do that. Okay, it's having issues. But anyway, you can see this large area here of interaction versus a very small area of interaction. And these are the exact same molecules, if you notice here, in terms of what's present. Both of these have 5 carbons, and let's see, is that 12? Yeah, 12 hydrogens. Yeah. 5 carbons, 12 hydrogens. The exact same stuff is present, but this molecule will have much stronger dispersion forces, which means it'll have a higher boiling point because there's more surface area where the molecules can interact with each other and push each other's electrons around. So larger, squishier, so to speak, molecules have more, they're more easily polarizable, which is to say it's easier to push their electrons around, and so they tend to have higher dispersion forces, which means a higher boiling point, and melting point too, for that matter. Melting point follows the same trend, it's just a lot more prominent in the boiling point. Alright, last thing here before we finish up this video. Which of these two, Cl2 or I2, do you think will have greater dispersion forces? So think about that for a second. Pause the video if you need to think about your answer, and I will let you know in just 1 second. I2 is going to have the greater dispersion forces. And the reason for this is very simply that it's bigger. It is a bigger molecule. If you have larger molecules or larger atoms, in general, we are going to say that those will have stronger dispersion forces. Now, if you have two things that are very similar in size, they don't have to have the exact same atoms, but if their molecular weight is very similar in size, then we might have to go to the shapes of the molecules to try to figure out which one would be stronger in terms of dispersion. But if one of them is significantly larger in terms of the mass, with very few exceptions, and none of which we're going to worry about, those larger molecules are going to have stronger dispersion. Alright, let's leave it there for this video, and the next one we'll pick up with dipole-dipole forces.